we're going to continue to take a look at one quantitative data, and we're going to look more at the measures of spread in this lesson. So these are kind of the things that we're going to talk about. Standard deviation, z-scores, the 5-number summary, range in the inner quartile range, and percentiles. So once again, we're going back to that movie data that we looked at in the last lesson. Your standard deviation is really just a number that kind of tells us how spread out our data happens to be. Now, the formula for standard deviation is like this here. Basically, it's saying you need to go ahead and take the difference between your data value and your mean. You need to do that for all of them. After you take your data value minus your mean, you need to square that. Take your next data value minus your mean, square that. Your next data value minus your mean, and square that. And do that for all your data values. This funny looking E says you need to add all those squared numbers together. Then you need to divide it by your sample size minus 1, get that answer, and then take the square root. It can be done by hand and with a calculator, but it's not exactly something we typically do because it requires a lot of work. Most of the time we use technology to do this. Now, your standard deviation of a sample is S, where standard deviation of your population is the Greek symbol sigma. So standard deviation gives you a rough estimate of the typical distance between the data values compared to the mean. The larger the standard deviation, the more variability there is in the data. In other words, it's spread out more. The smaller your standard deviation, the more compact your data is, and that's what you'll see here. Here, our data is relatively close to our mean. They're both symmetrical, both bell-shaped, but here our data is relatively close to our mean. Our standard deviation is small and close to 1. Here, our standard deviation is 4. You'll notice looking at your data, it's a lot more spread out left and right, so therefore it's a higher standard deviation. 95% of your data, if your data is symmetrical, or I mean not symmetrical, bell-shaped, should fall within 2 standard deviations of your mean. So in other words, if you take your mean and add 2 standard deviations and your mean minus 2 standard deviations, in between those two numbers you get will be 95% of your data. So here's a visual looking at a bell-shaped graph. Here's your mean. You go 2 standard deviations above, you get this. 2 standard deviations below, 1, 2 standard deviations below. In between these two numbers is 95% of your data. So if we're looking at this one here, if our standard deviation is 1, we go 2 standard deviations above. Here's 1 standard deviation. Here's a second standard deviation, up to 2. 2 standard deviations below would be to -2. So from -2 to 2 is 95% of our data. Standard deviation here is 4, so we go to our mean at 0, go 4 above, so we go 4 above. Here's 1, go 4 more would be up to 8. Going the other way, we go back to -4, then we got to go back another -4, gives us -8. So between -8 and +8 is 95% of all of our data. Now this can be done with StatKey, and I'll be doing that in a separate video, so you can just watch that. Now, we can look at this one here, and we want to estimate the standard deviations of hours of sleep. Well, I would say as we look at this, our mean is about 6 hours. If we go from about 2 all the way up to 10, in between 2 and 10, that's the majority of our data, which I would say is about 8. So you're going about 4 on each side. So if you're going 4 on each side, if you go 4 here, and it's supposed to be 2 standard deviations, it means each standard deviation is about 2. Actually, for this data, it's 2.03. But we're just estimating, and it is close to 2. So here we have a survey on pulse rates. The data is bell-shaped. we have our mean, we have our standard deviation. What is the interval that will likely contain 95% of the pulse rates in this sample? Well, we'd have to do two standard deviations. We'd have to double this. Well, if we double our standard deviation, we get 24.4. So we'd have to go and add 24.4 onto our mean and subtract 24.4 from our mean. In between those two numbers, we would get our 95% of our data. So if you take 2 times 12.2, that's 24.4, and add that onto this mean, that's where the 94 comes from. If you take 2 times your 12.2, which is 24.4, and subtract it from your mean, that's where the 45.2 comes from. We also want to go ahead and look at a z-score. A z-score for our sample is your data value minus the mean of the sample over the standard deviation of the sample. We also have z-scores for your population. We're going to go ahead and replace your x bar with the mean of your population, which is mu, and s, the standard deviation of the sample, with sigma, which is the standard deviation of the population. These are your z-score formulas. You'll use the top one if you're using a sample. You'll use the bottom one if you're using your population. But it boils down to just taking your data value minus your mean over your standard deviation. So z-scores kind of put everything on a common scale. It really allows you to compare apples and oranges. Two totally different things you can really compare because you put them on a common scale. And it's really how many standard deviations the data is from the mean. Values farther from zero are more extreme and will have a bigger excuse me, z-score. So a z-score is just the number of standard deviations that a data value falls from the mean. If it's positive, it's above the mean. If it's negative, it's below the mean. In a bell-shaped distribution, 95% of all your data fall between the z-scores of 2 and negative 2. So, in this one here, let's go ahead and try to figure out which one is better. A 28 on your ACT or a 2100 on your SAT. Well, the mean of your ACT is 21 with a standard deviation of 5. The mean of your SAT is 1500 with a standard deviation of 325. We're going to assume, to work this out, that these are bell-shaped distributions. And if you'd actually look at your data for this, yes, it would be that, but you weren't given that. So we'll continue on here. Looking at your ACT, you'll go your 28, which is your data value, minus the mean of the ACT over the standard deviation, which gives you 7 over 5, which is 1.4. So 28 is 1.4 standard deviations above the mean. Your SAT of 2100, you take 2100 minus the mean over your standard deviation, and you get 1.85. So because this has a higher z-score, we know that a score of 2100 is better because it's farther to the right, which is a better score. If we look at the visual aspects of it, your ACT score of a 28, which we said was 1.4, goes to here. 1.4 standard deviations above. For your 2100, it's 1.85 standard deviations above. You'll notice it's farther to the right. It includes more of your data. In actuality, this is about 97%. So a z-score of 2100 is your 97th percentile, meaning a z-score 2100 does better than 97% of the people that took the test. Whereas z-score of 1.4 for your ACT 28 is only the 92nd percentile. But we'll talk about those percentiles a little bit more later. So other measures of center, you have your max and you have your min. Max is your largest data value, min is your smallest. We also have quartiles. Now remember M is your median. It cuts your data in half. Well, if you find the median of that lower half, that's your first quartile or lower quartile. If you find the median of that upper half, that's your third quartile or your upper quartile. We also have the 5-number summary. We have our max and our min, we have our median, and then we have the 2 quartiles. And that really goes ahead and divides our data up into 25 percentile increments. Between our min and our first quartile is 25%. Between our first quartile and our median is 25%. So in other words, from your minimum up to your median is 50% of your data. Between your median and your upper quartile is another 25%, and so on. Measure of spread is how we talked about standard deviation. That's one measure of spread. Another measure of spread is your range, which is your max minus your min. The largest value minus the smallest value. We also have your interquartile range, which is the difference in your 2 quartiles, your biggest quartile minus your smallest quartile. Now your max and min is affected by outliers, so it's not resistant. Your interquartile range is really not affected by outliers, so it is resistant. So let's talk about comparing. When we are looking at measures of the center, we have our mean and we have our median. We have our measures of spread, our standard deviation, our interquartile range, and our range. We often use the mean and the median because they are calculated based on all the data values that we have. We can still use these other things, but it's often the mean and standard deviation that are used and recorded.